Hi again. We're back to talk about chapter 18 this time. We finished chapter 17 and said a number of things about temperature and getting temperature to change. We had an equation from chapter 17 that you're using in this week's lab that relates the quantity of heat that is required to change the temperature by delta T of a mass m of some substance that has a specific heat capacity. We also said that we could define a molar heat capacity where we need to know how many moles there are and what the molar heat capacity of that substance is. And that definition sort of accidentally trips us into needing to know how the individual molecules, because that's what we're counting when we count moles, how the individual molecules together manifest the sample, right? So that this thing that we're changing the temperature of, it exists, right? It takes up some volume, it has some mass. It does in fact have a temperature. There's some pressure maybe if it's a fluid. So where does the pressure come from? Where does where how do the individual molecules do the job of looking like a single, macroscopic object? And that's what chapter 18 is all about. It's trying to find a relationship between the microscopic and the macroscopic. Keeping track of the properties of a sample that we can observe, that are macroscopic, that we can actually, sort of engage with as humans, is it means that we need to either think about, if we can't express it explicitly, or maybe we get lucky. Maybe things are well enough behaved that we can actually write down an equation of state, an equation that interrelates the properties that we can observe. We've talked a little bit about the volume of an object. And let's say it has some primary volume. If the temperature of this object were changed, then the coefficient of volume expansion that we talked about in chapter 17 would, if our temperature became T when it was T0 and our volume was V0, then the coefficient of volume expansion would let us know what the new volume is. But it's not the only volumetric change we've bumped into. Think back to chapter 11 when we talked about stress. Bulk stress, right, changes the volume fractionally according to, there's some delta V out of V0. So there's some other term here that we need to worry about for a difference in pressure acting on the outside from, changing to P from some P0. And we need the compressibility of this material. As the pressure goes up, the thing would compress, so the volume would decrease. And this is, a rough idea of what we're talking about. We're interrelating the volume, temperature, pressure, and we're going to assume that the amount of this solid, it's a block of aluminum or something, that the amount of it, the mass or number of moles, is constant, that we're not changing that. This is the sort of thing we're thinking about. And now, we have this idea. We have one for solids. Let's see if we can get one for a gas. And there are three things we know from experiment about gases generally. We know that if we keep the volume constant, as we increase the temperature, we increase the pressure, which makes sense. If you've got, this is why they say not to put aerosol cans in, near hot stuff. If you increase the temperature, the pressure inside can build to the point where it explodes, and that's dangerous. If we keep the pressure constant, so just we'll do it this way. If we keep the pressure constant, then changing the temperature means the volume increases. Which, again, makes sense. Suppose we have well, I don't know if it makes sense, but it's a thing that we observe, right? I mean, I don't want to make too many judgments about this from, before we actually get at, or what does the temperature have to do with the volume? Theoretically. Experimentally, we know this to be true. And when we can run this experiment, if we have some sort of container, and we've got a piston that covers, like a lid, a tight lid. If we increase the temperature, but allow make sure that the pressure stays the same, the only way we can do that is by lifting moving the lid up the walls of the container so that the gas has more space in here. Experimentally, this is what we end up with. If we keep the temperature constant, the last thing we know is that as we increase the volume, the pressure decreases. Give the molecules of a gas more space, generally they're not contained as strongly, and they have no need to push on the walls of the container, because remember, that's what pressure is force applied over area. Okay, so pressure is proportional to temperature. Pressure is proportional to temperature. Volume is also proportional to temperature. So as temperature, volume, and yeah, that's right. Okay, great. That's the story. That's what we know from experiment. There's one more thing we know, and that's that if we increase the amount, if we increase the number of molecules, think about blowing up a balloon, either the pressure increases or the volume increases, or both probably. So I expect the number of moles to show up on that side, that if we increase that, we got to increase this as well. Yes, so the same temperature, keeping the temperature constant. And that's the story. that if we get this P down, PV over NT is equal to some constant. We just need a name and a number for that constant. The gas constant, and its value is 8.314 joules per mole Kelvin. Joules because the numerator here is pascals or newtons per square meter times meters cubed, moles and Kelvin for the temperature, but the meters cancel, but newtons times meters is joules, so that's joules per mole Kelvin. This isn't news. This is the you've seen this before. The ideal gas law. P V equals N R T, and that's an equation of state for an ideal gas, a well-behaved gas. One, well, what does that mean? We'll talk about that in a second. But for gases, we're going to assume that they are well behaved, or at least behaved well enough to be described by the gas law. We know that the number of moles is the number of molecules divided by the number of molecules per mole, Avogadro's number. RT. So these two things are just numbers, the gas constant and the, Avogadro's number. If we divide the gas constant by Avogadro's number, we can generate a new constant, KB for Boltzmann, Boltzmann, 1.38 times 10 to the negative 23 joules per Kelvin. Okay, cool. What else is useful about that? So the ideal gas law lets us talk about gets us an equation for the density of a gas if we express the number of moles. So that should be the mass of the sample divided by the molar mass, which we said in the last chapter that was going to be capital N. The mass that we have divided by the molar mass gets us the number of moles, N, R, T, pressure, volume, but the mass of the sample divided by the volume, M over V, pressure, molar mass divided by RT, but M over V, that's density. So now we've got an expression for density in terms of the pressure, temperature, and molar mass of a gas, which is pretty cool. The ideal gas law makes some approximations, makes some assumptions, which I think maybe it's obvious because we're calling it the ideal gas law. Ideally, this is how things behave. Is it actually how things behave? Uh, well, it depends. How accurate would you like your model to be? And we've spent some time over the last several weeks thinking about models and ways to describe reality. Could we be more accurate? And the answer is yeah, of course. Or at least we could make fewer assumptions. The ideal gas law has written the container has a volume V, and we don't care at all about the size of the molecules themselves. Really, if there are this many moles of molecules, those molecules themselves take up space within capital V. So those molecules don't really have V to move around in. They're contained in a space that is somewhat smaller because the molecules themselves have taken up some of that space. So if we wanted to be more, less assumptive, we could use the corrections according to van der Waals. Let's talk about the correction to the volume first. Instead of just V, let's make it V minus NB, where B has to do with the size of a molecule. Or, yeah, the size of a mole's worth of molecules, the actual physical space taken up by those molecules themselves. The container has a volume V, but we've got to subtract whatever space the molecules themselves take up. The other correction van der Waals proposed was to the pressure, and that is this term is a correction that is getting at the idea that the molecules actually do interact. That in the ideal gas law, we're actually making some assumptions about the fact that the pressure has nothing to do, that we can increase the pressure and those molecules won't see each other at all. The van der Waals equation of state is another attempt to interrelate pressure, volume, temperature, and amount. And it's those four things: pressure, volume, temperature, and amount. Moles, mass, molecules, something. That we're looking to interrelate with one of these equations of state. Okay. I'll stop a segment there. We still have, so there is a macroscopic pressure, there is a macroscopic volume, there is a macroscopic temperature. The number of molecules, I guess, well, it is what it is, right? The number of moles, it is what it is. But the pressure, volume, and temperature, how is it that they are related this way, I guess or if they are related this way, what does that mean about where they come from? What causes pressure? So our job for the rest of chapter 18 is to look at one very successful model for how the microscopic properties manifest the macroscopic ones.